I would like to present now a video illustrating the outcome of such a mesoscale simulation on this slide. Specifically, this will be a fluidized bed in which warm air is fed at the bottom and fluidizes a bed of particles. Liquid in the form of small droplets are injected above the surface of the bed with the goal to wet the particles. On the left you see the local droplet loading, here denoted as μ_lic. In the center the vapor loading, μ_vap, and on the right the temperature. You can nicely see that droplets are very localized and that the temperature of the incoming warm air is quickly absorbed by the particles due to their huge mass and their relatively large surface area. We now make an excursion to a bit more exotic physical model. The first one is radiative energy transfer. You have seen this application already at the beginning when comparing a resolved and an unresolved gas particle simulation, specifically in the work of Jäger et al. A simple but often suitable radiation model is the P1 model, which was documented and applied to dense gas particle systems by Mačák et al. The P1 model is a continuum model that predicts the radiative intensity G in a multiphase system and which reads as shown here on this slide. As you can see, it is a diffusion-like equation with capital gamma superscript rad being the radiative diffusivity. Kappa is an absorption coefficient. On the right hand side we have the emission contributions from the fluid and the particles. The latter is denoted here as EP rad. The equations defining the diffusivity as well as the effective scattering coefficient sigma f are shown here. It is just important to not confuse sigma f with the Stefan Boltzmann constant sigma sb. All other details can be found in the work of Mačák et al. The equation at the bottom left specifies how to calculate these coefficients. You see, they depend on the particle radiation properties Qx, Q scar and Q ups, as well as the particle size, the particle volume fraction, and the volume of the RVE delta V. The emission from the particles can also be evaluated relatively easily. Once we have solved the equation for G rad, we can then evaluate the source terms in the particle's energy equation to account for radiation phenomena. I would like to note in passing that there are alternatives to the P1 model when having radiative energy transport in CFD-DEM simulations in mind. One such alternative is the usage of a particle-particle radiation model or few factor based model as documented by Forkbear, Tausendschön and co-workers. These models assume that radiative transport is happening only due to particle-particle interactions, and these interactions are quantified by the so-called few factor. Since each particle pair within a certain range must be considered, these few factor based models are computationally more expensive than the P1 model. They offer, however, a potentially more precise solution to the radiation problem. Now, enough from radiation. Let us now progress to the particle side of a CFD-DEM model. And hence the next question. How do the equations look like that describe transport due to particle motion? Fortunately, the answer is relatively simple. They can be formed in a simple way. And here you already see the general form of such an equation. For each scalar quantity, we have to write an ordinary differential equation with a sum of all source terms on the right hand side. Thus, we just have to loop over all neighboring particles and phases, with J being the running index, and sum up the sources or sinks. If we discretize the particle internally, e.g. by considering multiple spherical shells making up each particle, we then write an ODE for each of these shells, of course. We can even account for intraparticle transport processes, e.g. intraparticle heat conduction. And exactly the latter was done in the simulations that are illustrated here on the bottom left. Forkbear et al. Have performed extensive simulations of granular shear flows under the influence of a heat source and heat exchange with an ambient fluid. As you might anticipate, at high particle conductivities, i.e. low Biot numbers, the core and the shell temperature of the particles is quite similar. The per particle temperature fluctuations that you see here are caused by the relatively large particle speed in this case. You will see in their publication that a high Peclet number was used for this purpose, which means that convective transport due to particle motion was stronger than heat conduction. On the right hand side, the Biot number is larger. As you can see, the temperature distribution is very different, simply because high Biot number means strong cooling. You can also see that core and shell temperatures of the particles near the bottom and at the top are quite differently. This is also what we expect and what this type of DEM simulations can provide. This also completes our scalar transport part of this multiphysics unit. We now switch to another physical phenomenon relevant for coupled fluid particle simulations, and which is structure mechanics. Therefore, let us consider a flow situation as sketched here in the image that was taken from Jourdakis et al. This is a classical benchmark for this type of simulation models and consists of a fluid flow domain, shown here in blue, and an elastic structure that is attached to the bottom wall and shown here in red. First, we have to think about the governing equations for the elastic structure, and we show it here at the right. Note, same as for all other governing equations, we have to supply appropriate initial and boundary conditions. For the sake of brevity and clarity, we have not included them in our slide, but simply refer to the literature, for example, to the book of Log et al. Same as before, the left-hand side contains time derivatives. In this case, it is the second time derivative of the displacement u dispel, which has the units of meters. Hence, the left-hand side has the units of force per cubic meter, since we have to multiply u displace with the density rho of the elastic material, as you see here. On the right-hand side, we have nothing surprising. We have the divergence of the stress tensor sigma. The latter has to be closed with an adequate material law, which uses information from the deformation tensor. Details are not shown here, but relatively easily available in the literature. Also, we have a volumetric body force term here, B, and that could be, for example, a term that involves gravity. And this is it already with the equations part for our structure mechanics short excursion. Let us now have a brief look at two interesting results. First, this is the velocity distribution around the elastic structure. As you see, the structure reduces the cross-sectional area and hence the flow speed must be larger directly above this structure. Also, and this is the main reason why we include structure mechanics, the structure bends significantly to the right. Of course, by changing the elastic properties, more extreme deformations can be predicted, and of course in a dynamic, so transient way as well. Just imagine the elastic structure here starts to vibrate. Our model could easily predict the frequency and amplitude of this oscillation. This slide allows us to look at a situation in which we also have particles in the fluid. The authors call this a six-way coupling. Since all interactions between particles, fluid and an elastic structure are considered and fully, meaning two-way coupled. As you can see, really complex systems can be modeled once we bring together the DEM with CFD and structure mechanics. Excellent! This completes our excursion to what is feasible with coupled CFD-DEM simulations, and I hope you liked it.